So we talked about that idea of the count and the name in Monday. You might be looking at saying, okay, that's kind of interesting, but how does that tie in with the calculations that we do? Well, the thing that ties it all together is the concept of place value. Place value is, that old concept that we learned, the name of each of the digits of a number. Starting at the decimal point, what's this last little place value here? Careful. First one is ones, then it's tens and hundreds. Those are actually the only three place values. They get repeated over and over again. Ones, tens, and hundreds. And ones, tens, and so on. This first group is just our base group. The second group of three is the thousands group. And then it's the millions, and so on. Now, when you name a place value, you name its value and its group. So this one would just be the tens place, but this one would be the 10,000, and so on. So if I have a number like 2836, each digit you pronounce the digit and its place value. It's not always just that specific, but this is 2,836. So each digit you're naming its place value. When we look at this number, 2836 is how we're used to seeing 2,836. But that's just an abbreviation. As what most of what we do in math, what we've been taught in math, it's a shortened version or an abbreviation. The full form of that number would look like this: 2000s and 800s and 3 tens and 6 ones. A lot of us have heard that called expanded form. It's really the full form of the number. When we look at it that way, it becomes obvious that each digit is a count. This is 2, and a name. It's thousands. We have 2 thousands. We have 8 hundreds. And when we see them like that, a lot of the things we're going to do with them, based on what we learned on Monday, the processes of addition, subtraction, multiplication, and division make more sense. Now, before we get to that, there are some basics we want to talk about. I'm not going to insult you by, translating, writing out a bunch of numbers and going through how you pronounce them. I'm going to assume you guys can pronounce a number and take the words and write it as a number. But one other thing where these place values are important comes in rounding. Let's say that I give you 4,856, and I ask you to round to the nearest 1,000. Now, most of you know how to do that, but before we actually do it, let's look at what that means. When you're being asked to round to the nearest 1,000 or nearest whatever, it implies that we're working on a number line. When it's round to the nearest 1,000, that's telling us we have a number line that is labeled in thousands. So this would be 3,000, 4,000, 5,000, pretend these are equally spaced, 6,000, and so on. And our number, 4,856, is on the number line. That'd be somewhere here. When we're saying round to the nearest, it's really talking about physically on this number line, which 1,000 is the closest or the nearest. That would be 5,000. So 4,856 to the nearest 1,000 is 5,000. Now, I don't expect you to draw out a number line every time you need to round something. So 4,856, we were taught a shortcut for rounding, which involved, first of all, identifying the digit in the thousands place. Which digit's in the thousands place here? The 4. Then we look at the next digit, because that next digit tells us, the 4 tells us we're between 4,000 and 5,000. That next digit tells us where we're located in there. The 8 tells us we're way up here, closer to the 5,000, so we're going to round up to the 5,000. In fact, anything 6, 7, 8, or 9, those are definitely closer to the 5,000. Those would all get rounded up. 1, 2, 3, and 4, of course, are all closer to the 4,000. Those would get rounded down. The difficulty comes with the 5. Let's say that this were 7,521 to the nearest 1,000. So the 7 is in the thousands place. That's telling us it's between 7,000 and 8,000. We look at the next digit, though, it's a 5. 5 is right in the middle. Well, what do we do with it? We still round it up. We were always taught to round the 5s up. There's a couple of reasons for that. One is you got to round them some way. And 2, if you look at that, 7,521, this was 7,000 and this is 8,000. 7,500 is right in the middle. Well, 7,521 is actually slightly past the middle. So it really is closer to the next one up. So when you see that that next digit is a 5, we always round it up because technically it is closer to the next one up most of the time. The only way it wouldn't be is if it was exactly 7,500. Then it is exactly in the middle, but we still need to do something with it anyway, so we round it up. Another thing that comes from, not necessarily from the place value, but from these number lines, is you might be asked to compare, like 6 and 13. You might be asked to put in one of these symbols. This is the less than symbol, greater than symbol, and equal to symbol. Well, if you look at the 6 and the 13 and you're comparing them, what it's asking you to do is to find them on the number line. 6 and 13 might be something like that. And tell me, what side is the 6 on? Well, if I look at it, 6 is on that side. The arrowhead on that end of the number line looks like that. That's where the less than symbol came from. It's the arrowhead on the left end of the number line. So this is saying 6 is on this side of 13, or less than 13. Now, there are all sorts of shortcuts we were taught, like this is the alligator, and the alligator eats the bigger frog, or the bully points and laughs at the little guy, or whatever. And there's all sorts of little tricks you learn that help you remember which way those symbols are. But that's where they actually come from, is the end of the number line. 6 is on this side of 13. If I had 7 and 2, what symbol would I use? Well, that one, because 7 is on that end, that side of the 2. Okay, let's move on up into some operations. Now, first thing we're going to look at is, we've looked at the count and the name. I want to take just a second and look at the amounts, looking at the counts, combining the counts for a while. And the operation of addition. Addition, and this is going to be a very complex definition of addition, but it's going to help us out later on. Addition is the operation of combining things. 3 plus 5. But really, to combine things, we have to understand what represents the amount. Now, we're just talking about the amounts, not the name, just the counts. What really does the amount of 3 mean and the amount of 5 mean? Well, it goes back to this number line again. 3 is represented on the number line. We could just put a dot at 3, but that's not useful for operations. 3, what we use is something called a vector. And all it is an arrow that starts at 0 and goes to 3. That represents the value 3. 5 looks like this. Starts at 0 and goes to 5. That vector, that arrow, represents the value 5. And when we're doing addition, what it's telling us to do is to take those two vectors and put them together, combine them. In other words, put them end to end. So when we put them end to end, we end up with 8. So that's how when we add 3 and 5, we end up with 8. And many of you probably did see counting on the number line and stuff like that for addition. That's what we're really doing, is making those vectors on the number line. Again, I'm not going to insult you by going over basic addition facts. I'm going to assume you guys know how to do basic addition. But I wanted to go over it a little bit because at some point we're going to talk about negative numbers, and having this visualization for adding numbers is going to help us a lot with the negative numbers. So let's now step up into adding larger numbers. You know, we talked about the count and the name again in the last class. We said the place value is what ties that all together. Let's look at that. If I have 437 plus 242. Now remember, we said that those are just abbreviations, so I'm going to write them out in their full form. So 437 is going to be 4 hundreds and 3 tens and 7 ones. 242 is going to be 2 hundreds and 4 tens and 2 ones. We also said on Monday that when we add numbers, add or subtract, we can only combine things that have the same name. And we just mentioned earlier, when we write it this way, we can see that every digit has its account and a name. So like the 3 tens here, when we're adding or subtracting, can only be combined with the 4 tens. And the hundreds can only be combined with other hundreds, and ones with other ones. At some point you were told that when you add or subtract large numbers, you have to make sure you line up the columns, right? And the reason for that is because, as we've said, you can only combine things with the same name. And that goes right down to the place values of individual digits. You can only combine digits that have the same place value when we add or subtract. Once they're lined up, all we have to do is, well, 4 plus 2 is 6 hundreds. 3 plus 4 is 7 tens. 7 plus 2 is 9 ones. So that's 679. Well, some of you might be looking at that thinking, he did that backwards. I started on the left and went to the right. We normally start on the right and go back to the left. Why do we go that direction? Well, because in case we have to carry. Then we might have 475 plus 259. We start on the right and work our way back to the left because we can run into things like this. 5 plus 9 is 14, so I'm going to keep the 4 and carry the 1. 1 and 7 is 8, plus 5 is 13, so I'm going to keep the 3 and carry the 1. 1 and 4 is 5, plus 2 is 7, so 734. That's that process of carrying. Now again, I'm not going to keep doing examples of that because I'm going to assume you guys can add. If you're not great at adding, I know a lot of you probably going to end up using the calculator with it, and I'll talk about that in a minute. But I wanted to go over this for a couple of reasons. One is to show you, to make sure you've seen it done. 2, to show you that that's not the only way. A lot of us have been taught in math that there's only one right way to do things, and there's not. I could actually show you 3 or 4 different ways of adding numbers. It's going to work every time. But let me just go over one other method. This process that we just saw here of carrying and going right to left is actually relatively new. It's only about 150 years ago that they started doing things that way. Before that time, what they would have done when they added these numbers is they would have done 4 plus 2 is 6. 7 plus 5 is 12, so 2 drop the 1. 5 and 9 is 14, so 4 drop the 1. 6 and 1 is 7. 2 and 1 is 3, and 4. We get the same answer. In fact, in some foreign countries, they still teach addition that way. And actually, there's a couple other ways I could show you, but I'm not going to confuse you. I don't expect you to change the way you add numbers or anything, and I'm never going to ask you to remember this. The point is to show you that you've always been given the impression there's exactly one way to do things. There's not. There's usually several different ways you can go about getting an answer in math. And as I mentioned, I realize the calculators are there and they're probably going to be used. When you do, though, when you go to punch in the calculator, I do hope that you look at this and say, okay, 475 is about 500. 259 is about 300. 5 and 3 make about 800. I'm hoping for an answer close to 800. 734 makes sense. Because if you're like me, I have these kind of fat sausage-like fingers. It's easy for me when I'm pushing buttons on that calculator to hit an extra key and not realize it. Would not be uncommon for me to punch in something like this and get an answer like 2,634. Well, if I'm paying attention, I know that's wrong because it can't be bigger than 700 or 800. But if I'm not paying attention, I write down that answer and I go on with life, and then there's problems later. Let's look at subtraction. Now, I'm not going to write it out in the long form because I think you guys get the point by now that it's the place values of those digits that are the names. We can only add or subtract things with the same names. So just like with addition, we have to line up those columns. And once they're lined up, we subtract. 7 minus 5 is 2, 3 minus 2 is 1, 8 minus 6 is 2. It's 212. Now again, you probably noticed I went left to right. We normally go right to left in case we need to borrow. Talkative group. So 847 minus 298. We run into something like that. We would go starting on the right, going back to the left so that we could borrow. 7 minus 8 can't be done, so what do? Borrow from the 4, that's a 3. This is now a 17. 17 minus 8 is 9. 3 minus 9 can't be done, so we need to borrow again. That'll be a 7, and this will be a 13. 13 minus 9 is 4. 7 minus 2 is 5. Now again, just like the addition, that borrowing is a relatively modern process. One other way that it could be done, it was done, I said 150 years ago or so. He's done 8 minus 2 is 6. 4 minus 9 can't be done, so borrow from the 6, that's a 5. This is 14. 14 minus 9 is 5. 7 minus 8 can't be done. Borrow from the 5, it's a 4. This is now a 17. 17 minus 8 is 9. Comes out the same. So again, I don't expect you to change how you subtract. I just wanted you to know there's another way of doing it. And again, I realize that you look at this is probably 800. This is about 300. I'm expecting that to be about 500. So when you punch that in the calculator, you know before you start that you're expecting an answer around 500. So this looks reasonable to you. Well, let's look at multiplication quick. Let's do 32 times 21. And this I am going to write out in the long form. When we multiplied, we said we don't need the same name. So what that means is the ones here not only can multiply the other ones, but they can also multiply the tens. In fact, every digit in one number can multiply every digit in the other number. And that's all that long multiplication is just an organized way of making sure every digit in one number gets combined with every digit in the other number. For example, what we usually do is we start with the last digit in the bottom number, and we work our way up into the top number going backwards. So the 1, 1 times 2 ones. We combine the counts. 1 times 2 is 2. Then we also combine the names. Ones times ones is ones. When we're adding down those columns, and we just keep the same names, so the names just drop down. But when we multiply, we do have to remember to combine the names as well. So next we have to do the 1, 1 times 3 tens. 1 times 3 is 3. Ones times tens is tens. So now we're done with the 1, 1. We're going to move over to the 2 tens. What have we always been taught we have to do down here now when we moved over that digit? Put in a 0 or leave a space there, right? The reason for that's going to become apparent here in just a second. So now we have 2 tens times 2 ones. We combine the counts. 2 times 2 is 4. Tens times ones is tens. We needed that 0 here, or we needed to move over to make sure that our tens lined up with the other tens. Now we have 2 tens times 3 tens. 2 times 3 is 6. Tens times tens is hundreds. So you can see how the place values fall into place there. And then, of course, we're going to add. We got the 2 ones, 3 and 4 make 7 tens and 600. So 672. Now, once again, I realize, especially when it comes to long multiplication, you're probably going to use the calculator when you can. But still, look at that as 32, or look at that as 30 and 20. 3 times 2 is 6, so you're expecting that to be about 600. The last operation is division. Long division is the one operation that has probably been changed and polluted the most throughout the modern times. It looks very little like the actual process of long division. So what I'm going to do is I'm actually going to show you the real process of long division, and then I'll show you quick how it connects to the shortcuts we've been taught. But to do that, let's get a little background. We talked a little bit about that relationship between multiplication and division. So let's start with multiplication here quick. If we did 5 times 3, we know that's 15. But back in first or second grade, before you memorized the tables and knew that 5 times 3 is 15, how did you figure that out? Most of you probably did 5 plus 5 plus 5, right? Repeated addition. That's just saying 5 3 times, or 3 5s. So multiplication is actually defined to be repeated addition. Well, if division has such a close link to multiplication, then it would make sense 24 divided by 8 could be solved by taking 24 and subtracting 8. That's once. Subtract 8 again, that's twice. Subtract 8 one more time is a 0, that's 3 times. 24 divided by 8 is 3 because we can subtract 8 from 24 3 times. Division is just repeated subtraction. In fact, our remainder system comes from that. If I have 27 divided by 6, I take 27, I subtract 6, that's 21, that's once. Subtract 6 again to get 15, that's twice. Subtract 6 again to get 9, that's 3 times, and subtract 6 again to get 3, that's 4 times. So 27 divided by 6 is 4, because we can subtract the 6 4 times, with a remainder of 3 because there's 3 left over. Now at some point we're going to look at how do we convert that into a decimal or a fraction. For now, we just have the remainder. So with that in mind, let's look at a long division. $41,287 divided by 23. Now I just told you that division is repeated subtraction. But I'm not going to start subtracting 23 from 41,000. It would work, but we don't have that kind of time. Chances are you lose track of how many times you did it anyway. But if we could subtract a big chunk of 23s from the 41, that would speed it along. And that's exactly what long division is. What we do is you look at this first digit in the number we're dividing. What's the place value of that first digit? What's the place value of that 4? It's in the 10,000s, right? So we're going to take 10,000 times 23 would be 230,000. Can I subtract 230,000 from that? No, it's too big. So what that's telling me is I can't take a bundle of 10,000 23s and subtract them. So the next place value would be 1,000. 1,000 times 23, 23,000. Can I subtract that from up there? Sure can. I can only subtract it once, so I'm going to subtract it once. So subtracting 23,000 gives me 18,287. I just subtracted 23 1,000 times. My next place value would be 100. 100 times 23 is 2,300. Can I subtract that from what's left? Yes, I can. In fact, looks like I can do it a few times. 8 won't quite work. Let's go for 7. 0, 0, 1, carry the 2, 9, 11. Oh, that's not right. 14. 16,100. Looks like that's going to have to be it. So 16,100. Subtract that off. 2,187 is what's left. Well, what I did here is I subtracted 2,370 7 times. What I really did was I subtracted a bunch of 123s 7 times. 100 times 7 is 700. I subtracted 723s. Next, place value would be tens. 10 times 23 is 230. I can subtract that up here a few times. Will 9 go? 9 might go. Let's try it. 2027 or 2070. So I can do it 9 times. There's 7, 1, 1. So 117's left. But again, I didn't really subtract anything 9 times. I subtracted 23, a bundle of 10 times 9, or 90 times. And then, of course, the last place value is just the ones place. 1 times 23 is 23. I can subtract that from here. I'd say 5 times. Oops, 5 times. Which is going to give me 115. There's 2 left. So at that time, I did just subtract it 5 times. And there's a remainder of 2. So when I take 41,287 divided by 23, I get 1,795. I'm just adding these up with a remainder of 2. Now you might be looking at that thinking, I have no clue what he just did. That looks nothing like what I've done in the past. But it actually does. What we've been taught to do is this. We got the 23. Does 23 go into 4? No. So we leave it blank here. Well, that's what we did here. Can't subtract it 10,000 times. It's too large, so we just move on to the next digit. Now we go to 41. Does 23 go into 41? Sure. It goes in there once. Now 1 was the last digit we used, so we put the 1 above the 1. 1 times 23 is 23. We subtract. Now it still looks different, but at this point we actually can find the similarities. What we did here and what we did here are exactly the same thing. We just left out the zeros. See what I mean? So all that what we've done here is we've shortened it up. We've left off some zeros and we've taking up less space. And we're not actually thinking about this. We're just looking at the digits and trying to figure out what can go into them. Now I realize long division, again, is probably going to involve a calculator. It's the one operation I try not to do without a calculator if I have to, if I can avoid it. So still when you're looking at this, I'm hoping you're looking at this and saying, okay, that's close to 40,000. That's close to 20. That's going to be about 2,095. Any questions?
When I did it on the assignment thing,
Yep.
I would do the division, I would use calculator, and when it would have a remainder, it would tell me my answer was wrong.
Okay. Because your calculator is going to give you a decimal afterwards, and it doesn't want the decimal, it wants the remainder. So let me show you what to do with that. Let's say you have 59 divided by 7. You punch that in your calculator. 59 divided by 7 is going to give you something like 8.42857,143 approximately. Don't worry, it's not contagious. What that's telling you is it goes in there 8 times, but you got to figure out what the remainder is. So now you have to work this backwards. You're going to take the 8 times the 7, which is 56. 56 and 9, the difference is, or 56 and 59, there's a difference of 3. So what it's telling you is if you divided that by 7 and got 8, 8 times 7 is 56, there's 3 pieces left over. Remember, we're going back to that repeated subtraction. We're subtracting that 7. We can subtract it 8 times. That would be 56. We're left with 3. So what they're looking for is 8 with a remainder of 3, not 8 with a 0.428. Yeah. Yes?
Wouldn't you just take the number that's behind the 4, and if it's less than 5, that would be 4. If it was greater than 5, bring it up to 5?
No, because only if you're dividing by 10 does that work. If you're dividing by 10, that would work. But dividing by any other number, it doesn't. This is, now the other way you could do this, it's a little trickier, but the other way you could do this is this. You divide that out, you get the 8.4285, and I'll just do this on the calculator for you. I'll show you how it works. I do 59 divided by 7, and I get the 8.42857, blah, blah, blah. I write down the 8, that's part of my answer. I'm going to come back here and I'm just going to subtract 8. Make it go away. Now notice I didn't clear the calculator. I didn't type anything back in. I just subtracted the 8 to get rid of the whole number, the part in front of the decimal point. Now I'm going to multiply. I divided by 7. I'm going to multiply by 7 again. And it should give me back now the 3. There's a remainder of 3. So if I did 84 divided by 11, which will give me the 7.6363. So I write down the 7. That's the whole number. Subtract 7. And I'm going to multiply by the 11 again. Takes me back to a remainder of 7. So it's 7 remainder 7. Any other questions? You look a little bit confused yet. You're okay? Okay. Yeah, and really, it's a long division in remainders. All it is. When you do a long division, 59 divided by 7, it goes in there 8. 8 times 7 is 56. There's 3 left over. There's your remainder. To me, that's the easiest way to do it as well, but I realize that a lot of people are more dependent on the calculator than I am. But yeah, to me, that's the easiest way to do it. I'm sure that's probably about how you're doing it. Okay. Well, our next thing. Those are the 4 main math operations. There are other math operations out there that we tend to forget about or not to realize. We have powers and roots. All math operations come in pairs. And there's even a lot beyond powers and roots that we're not going to get into, like exponents and logarithms and stuff you'd get into if you're in an electronics course. All of our operations come in pairs. They're what we call inverses. Like addition and subtraction. If I want to reverse addition, I'm going to use subtraction, or the other way around. Let's say I start with a number. Somebody give me a number between 10 and 20. 20? Let's say I'm going to add 7 to it, what do I get? 27. What if I want to get back to 20? What do I have to do? Subtract 7. Good. Adding and subtracting are inverses. If I add a number and then I subtract the same number, it takes me right back where I started. Or if I had subtracted, let's say I started with that 20 and I subtracted 3, I'd get 17. But again, if I wanted to get back to the 20, I would add 3. I did the opposite of subtracting, is addition. They're inverses. If I subtract a number and then I add it back in, it goes back to where we started. Multiplication, same way. Give me a number between 1 and 5, or between 2 and 5. 4. Let's say I want to multiply that by 9. 4 times 9 gives me 36. If I want to get back to the 4, I have to divide by 9. Multiplying and dividing are inverses. They reverse each other. They undo each other. Multiplying by 9 and dividing by 9 will cancel each other out. Or, if I started with a 12, I divide by 3, I get 4. But if I want to get back to the 12, I have to multiply by 3. Again, dividing and multiplying are opposites. They reverse each other. Powers and roots are the same thing. We've seen powers. What does that mean? Well, 7 to the power of 2, or 7 squared, it means 7 times 7, or 49. What if it were this? 8 to the 3rd power. What does that mean? That means 3 eighths multiplied together, otherwise known as 512. First thing we need to do is figure out how to calculate these. On your calculators, depending on what calculator you have. On the Texas Instruments, the TI-30 one-line display, you'll have a key. It's like the 2nd or 3rd one down from the top over here that'll look like this, X to the Y or Y to the X. If you have the 2-line display, it's over here on the left side, and it looks like this. It's called the caret key. On the Casios, you'll have a button similar to that, and some of it might actually just be like this. 2 boxes, or X with the little blank box there. But it's going to work the same. Let's say you have to want to type in 5 to the power of 6. You would type in 5, You'd press whichever key that was, and then the 6, and hit equals. Should come out to 15,625. So if you have your calculator with you, double check that and make sure you can make it work out. Those of you that don't have it with you, guys, do you have calculators, or you still need to pick them up? Haven't got yours yet? Yeah. I mean, there will come a point where, even if you're good with the operations, there will come a point where you need it. What's the next class you're going to be taking? What, do you know what program you're in? Or, for business, you're probably going to take math and business applications, business math. So for you, the TI-30 would be perfect. The TI-30, get the 2-line display. The 2-line display just has an extra line, so on the screen it displays what you're typing in, and then when you hit equals, it puts the answer down here, so that you can see see it goes through. For the math with business applications, or business math class, we call it, there are some formulas that are long enough that the 1-line display TI-30 doesn't handle them all at once. You got to split them up, so that 2-line display makes it easier. And for most of you, that'd be the best calculator for what you're going to do. Did you get 512 out of that? You got it?
No, I don't know how to use this damn thing.
Okay, here, I'll come take a look quick.
Whoa.
Okay, so that's the powers, the exponents. The opposite side of that, then, of course, would be roots. We're just going to look at something like this. That symbol, it's called the radical symbol. We're used to calling it the square root. And it's used for square roots. The square root of 25, what that is doing is that's an inverse. What's really happening there, 5 to the power of 2, or 5 squared, is 25. That means 5 times 5. The square root is the reverse, or the opposite, of squaring, which means it's asking us to go backwards. That answer would be 5. So the way you think of it is when we ask like the square root of 16, what that's asking us is, what number squared equals 16? Well, what number times itself is 16? 4. Because 4 squared, or 4 times 4, is 16. Make sense? We will talk about roots a lot more later in the course. For now, we're gonna end it there. Let's take our break. It's a little bit early, but let's take a 10-minute break. We'll come back at about 9:25, and